Hi, looking just quickly this time at lesson 1.14 that talks about derived units. Today in this video, it's a very short time. I hope to help you identify and calculate derived units. So I'm going to do that using a variety of examples. Now, the difference between lesson 13 and lesson 14 is that lesson 13 talks all about what we call base units. Those units we talked about that are used to measure most commonly different units. So we said we use the meter stick to measure length, typically the unit of the kilogram to measure the mass of something, how much it weighs. Kelvin is our unit of temperature. Second is our preference for time in science. The mole, as we will learn or have learned now, is the amount of a substance. We said the candela and the ampere are kind of more physical chemistry terms, physics-wise. It describes light intensity and electrical current. None of these units describe two things. A derived unit is different from them. In a derived unit, we express multiple quantities, combinations of those quantities, to sort of create a new unit altogether, a new classification, a new description. So we can combine specifically, we can combine length 3 times to make volume. We'll talk about that. We can combine mass and length in multiple units to describe density, and those are really the ones we focus on in this lesson. So one example, or two examples, sorry, of a derived unit include area and also volume. Area is a derived unit because to calculate area of a square, for example, you need to take the length times the width. That would be 1 centimeter by 1 centimeter. Now the units there they're not just centimeters. You multiply 2 centimeters just like you would multiply two numbers, and the answer ends up to be in centimeters squared. So that squared unit tells you that it's a derived unit. It came from more than one unit. Same type of unit, two length measurements. As you can see here, centimeter measures length. However, when they're combined, we refer to them as a derived unit. The same thing works for volume. If we multiply 3 volumes together, we don't just multiply their numbers, 1 times 1 times 1. I think a lot of times you guys get to science and you're not used to putting labels for units on anything. So we asked you to do a derived unit and make sense of multiplying units together, and you're like, what? I don't even use units, right? That's probably why. If you multiply 3 centimeters together, your answer is not in centimeters, it's in cubic centimeters. And that cubic portion is what makes a derived unit. The word derived itself means to come from other things. So our derived units are new measurements, in this case volume and area, new descriptions of shapes, of geometry, that come from single individual length measurements. Okay, so when the metric system was invented, of course, the unit of volume was called a liter, which was derived from a cube of 1 decimeter on each side, so 10 centimeters on each side. 1 liter then equals 1,000 cubic centimeters. So I was talking in class briefly about derived units, and I talked about that cc's that you often hear in the hospital when they're refilling your IV bags. I need 200 cc's stat, or maybe in a syringe that they're putting into your IV line. 1,000 of those is equal to a liter. So typically in hospitals, they're dealing with about a liter of an IV bag, maybe half a liter. So they're dealing with about 1,000 cc's or 500 cc's. Density and concentration are also two commonly used derived units in science and especially in chemistry. The density unit is something you're probably more familiar with than you know. The units of density that we typically use are mostly grams per milliliter and grams per liter. And when we do the calculations, you will see that. However, because the cubic centimeter is really the original version of a volume, we do also have grams per cubic centimeter. And what we're expressing when we do that, write that slash, is really measuring a mass per volume. So that's the technique that's being used there. Mass, of course, is our grams, and volume we can measure in any way we want. We can measure milliliters, liters or cubic centimeters. Okay, so that's what's happening there. Density, of course, is very important property to substances. You can see down here mercury, the density of mercury, it's very, very actually heavy, even though it's a liquid. So it kind of helps define how it behaves. Density is a measure of how tightly packed and how heavy the molecules are in an object. So on the left here, you can see an example with very, very high density substance where we have lots and lots of molecules in a very small space that is a greater mass in the same smaller volume, I guess. And here we have less mass in approximately the same volume, but it's still kind of small. You guys are probably most familiar with density with regarding to things floating. So I did have a video. If I had taught this lesson, I would have shared that with you. In this cup, there are 3 substances: water, corn syrup, and vegetable oil. And I'd be a liar really to say I'm sure. I think I have to go by color here mostly. What happens is they start the video with the vegetable oil, which is actually on top. They food colored the corn syrup blue. So they had poured some vegetable oil in the cup, and then they poured in the corn syrup. Okay, and then what happened is they saw the corn syrup actually snuck right underneath the vegetable oil, and the water finally they added last, and the water went all the way to the bottom, because in this case water was the most dense. More dense substances sink. So when we talk about ice cubes in a glass of water, we say ice is less dense than water because it floats. So in this case, vegetable oil would be the least dense substance. Corn syrup is somewhere in the middle. And water was the most dense because it sunk. So in terms of understanding what density is, it's this right here. How many molecules fit into a size space. For water, lots and lots and lots of molecules fit into a small space because of its structure. And we talked about the fact that it can hydrogen bond and do intermolecular forces. Whereas oils, we learned about fats, they're kind of long and they're flimsy and they flap around and they're long chains, so not as many of them fit in the same volume so that they're able to float. But really, especially in lesson 1.14 for the quiz, you're mostly responsible for being able to calculate these things. So knowing the formula for density is important. The formula, of course, is m over v, that is mass divided by volume. And in many cases in this lesson, we were pretty straightforward with you. So a problem that reads like this: if the mass of an object is 35 grams, we would write that down immediately, mass equals 35 grams. And it takes up 7 cubic centimeters of space. That would be our volume, 7 cubic centimeters. Calculate the density. Well, if we've identified it, usually that's the hardest part here, identifying your variables m and v. And we've done that. So we're just going to go ahead then and substitute into that equation 35 grams divided by 7 cubic centimeters. And we do the math, of course, with the numbers. So we get density equals 35 divided by 7, which is 5. But we also do the math with the units, and that's the important piece here to this lesson, the fact that density is a derived unit because it comes from 2 different units. The answer would be 5 grams per cubic centimeter because it's how much weight or how much stuff in a certain space. And here we're comparing it to 1 cubic centimeter. So the correct answer would be A. Now this question comes, I believe, from your practice worksheet. I think it might also be in the quiz or maybe in the lesson. I'm not quite sure. It says a miner found a mineral fragment with a volume of 1.49 cubic centimeters and a mass of 28.7 centimeters. So I don't know if I'm going to use this information yet, but it just identified for me what's what, so I'm going to write that down. Mass is 28.7 grams, and the volume V is going to be 1.49 cubic centimeters. And then it tells me the density of 2 other substances. And it says, which mineral did this guy find? So basically, it's inadvertently asking me, well, if I know the density of these 2 things, I need to find the density of my mineral fragment and compare them. So let's do that. Density equals mass divided by volume. So we would have a mass of 28.7 grams, and we would divide that by 1.4 centimeters cubed. And I did not actually do this ahead of time, so I need to sneak out my calculator here. And it's using up my precious time to open it. Okay, taking a look, see, we have 28.7 divided by 1.4, and I get 20.5. 20.5 grams per cubic centimeter. So I believe the answer here would be the miner did not find either of these minerals. It's most close to gold. Maybe it had some impurities in it, but density is a characteristic. Oh, wait a minute. See? Do you see what I did here? This is all too common. I do this kind of stuff all the time, and it changes your answer, so that's bad. Okay, let's just take another look here. The volume should not read 1.4. It should actually read 1.49. It's going to change our answer slightly and definitely enough to matter here. So let me make some changes. See, I make mistakes too. You guys think you're the only ones. 1.49 centimeters. Let's try again. Get out our calculator. 28.7 divided by 1.49 gives us 19.3. And so we do end up actually with one of the answers that was provided, 19.3 centimeters. 19.3 grams per centimeter cubed is the density of gold. So which mineral did the miner find? He found gold. Lucky miner. Okay, there's a variety of examples in the course that you can revisit. This one asks you to calculate the mass of a 20 cubic centimeter sample by using the density. So here you would just rearrange the equation, density equals mass divided by volume, by multiplying each side by the volume. And what happens then on the right-hand side is the volumes cancel, and you're left with mass. And on the left-hand side, you have volume times density. So if you look at your units here, you have volume equals 20 cubic centimeters. You're going to multiply it by 13.6 grams per centimeter cubed. Let me pull this down here. And when you do that, your centimeters cubed will cancel because one is in the numerator, one is in the denominator. You're left then only with grams, and that's what you're looking for. You're looking for mass. So the answer here would be 20 times 13.6, which is 272. It's in mass, so we're looking for the answer in grams. We started in grams, so we're looking for the answer in grams. Okay, so knowing the density in some cases helps us calculate mass or volume, or vice versa. Concentration is also a derived unit. It's mentioned in the course. Most often we're looking at that as grams of solute. The solute is the thing that's usually being dissolved in a solution. And the solution, of course, is the total solution once things are dissolved. So how many grams or how much solid is in the entire solution? We will look at this later in the semester when we talk about solutions. It's not something we're going to do much with right now, but know that because we have, of course, again, two units put together, grams and liters, this is an example of a derived unit. This is probably the most, even though it might seem complicated, the most straightforward because it's the least amount of problem solving among the chemistry math practice that we've done in this unit so far. So you should be able to identify and calculate derived units. Again, identifying derived units is nothing more than looking for combinations of normal units. Specifically, this lesson focuses on density. Calculating derived units is just a matter of doing the number calculation and then carrying through as well with the units, multiplying or dividing.